Thank you. All right, good afternoon, everyone. So we heard a lot about, starting with Rob's talk this morning, how P4 is great as a formal specification language, and then how P4 is awesome at programming the data plane. So I'm going to talk about how P4 also is great at being a hardware abstraction language for control plane. And we've used it for switches in the past, and today I'm proposing that we use it for network virtualization on smart NICs as well. So I'll explain what that means. So P4 has played a dual role in switch SDN. We at Google used it as a HAL, as a hardware abstraction layer for our control plane applications. And it's been used as an SDK to program the actual data plane as well. And these two are related, but not exactly the same thing always. And we believe P4 has an even bigger opportunity on smart NICs as a HAL for network virtualization. It enables NIC optionality, helps us port our software. It can be a win for both NIC vendors as well as users like us and others. So let's go through that. Yeah. So first I'm going to talk about what we've been doing with this thing called SDN. Then we've deployed SDN at scale at Google, what we've learned through our experience in deploying P4-based switch SDN, and then the proposal for P4 HAL for network virtualization. So Google is one of the pioneers of software-defined networking. And these systems, they range all the way from traffic engineering, network routing, optical systems, transport protocols, and so on. And these systems are all deployed. This is a sliver of the work that Google has done in this area. And these days, a lot of it is focused on cloud and AI, two of our fastest growing consumers of infrastructure. So let's see how we've used P4. So P4, just to remind everyone, about a decade ago, it started about a decade ago. And this is a picture from the original P4 paper, So the idea is, it's a language to program packet processors. You take a P4 program that an SDN control plane compiles to generate a few artifacts. One of them is used to program configure the switch pipeline. And it also is used to generate an API that can be used by the control plane to program the rules into the switch at runtime. So that was the model proposed. So it enables reconfiguration of the switch. The switches, if they're fully programmable, can be protocol independence. And the control plane can be target independence. And many of these goals have been met in some shape or form, but slightly differently. So let's look at, this model works great if your environment is homogeneous or you're doing a greenfield deployment. But that's almost never a reality. We have heterogeneous environment. We're deploying things in existing data centers where we have existing switches that are not all P4 programmable. And we have existing applications that all need to continue to work as we shift to this SDN model. So what did we deploy? So this picture here shows on top is Google's SDN controller, a simple picture of that. It's called Orion. On the switch, we run a version of Sonic. It's called GPINs. And then you have the switch ASIC. So the Google's SDN controller, Orion, has, it manages a fleet of switches. And it has a model of those switches that's described in P4. So it has a model of, let's say, top of the rack described in P4, middle block, and other layers in the topology of our network. The controller when it wants to program something, it uses that P4-based model to program the switch. On the switch, there is a P4 runtime, which eventually translates things to SAI, which is the switch abstraction interface. That's a static interface defined by a consortium of players, which then is the backend of SAI is implemented using an SDK, which actually programs the switch. So if you see in this model, our P4 eventually gets translated to SAI, and the SAI is then what acts as a translation layer between the actual hardware and our controller, or the intent of the controller. But some vendors implement the backend of SAI using P4, so namely, Intel Barefoot, for example, but there are others too. So what have we, this model is now, being deployed at Google, and we think, we gain many benefits from it. But a question is asked, okay, if you have SAI, then why do you still need this P4-based HAL? Like, why are we doing this in our controller? Why not have the controller directly target SAI? We believe P4 does give us many benefits. But first, so first observation is that this P4 is being used in these two related but distinct use cases. One is that it is a HAL for our SDN applications. So Google has SDN controllers. There may be others outside. The P4 that our controller uses tends to be target independent. This has to work across multiple different implementations, a heterogeneous set of switches, whether they are P4 programmable or not. And in that P4, we tend to avoid vendor extensions. By definition, it's a HAL. We don't want it to be specific to any one particular hardware. The switch vendors have also used P4 to program their switches, but there, the P4 tends to be target specific. So you have externs and other ways to customize P4 to work well on their platforms. In addition, the same program, at the controller level may be expressed in different ways on different platforms. We heard earlier Krishna talk about, how things can go wrong if you add one extra pipeline in the stage. Now, our logical model of P4, the controller's model of P4 may not change, but the implementation may decide, okay, these two stages should really be merged into one, but our controller doesn't have to know that, because that will be different between one switch to the next. So this model of this decouple, these two different worlds of P4, they can exist independent of each other, with each other, and a small translation layer can bridge the gap between what the controller expects and what the switch provides. So now let's look at, so why do we do this? Really, we think we do get these many benefits. First of all, it does serve that purpose of being a great abstraction layer. Our controller is independent of the switches, and as switches change or code changes at the lower layers, switches maintain that abstract layer. But more importantly, like Rob said this morning, it's a formal specification. It comes with a behavioral model, and we can keep the implementation, the behavioral model, and the controller in sync via P4. So if you believe that P4 is a great way to express our specification, we believe we need to go one step further and actually use it in a controller as a HAL, so that the API that you generate from that P4 is the API that you're running the behavioral model against, is the API against which you're testing the real switches. If these two are decoupled, they can, again, go out of sync. And then tools like P4 Test Gen have helped us generate automated tests, which have helped us find hundreds of bugs in real switches, which, according to the vendors, no other customers of theirs had found. So these bugs had existed in their software, in their firmware, but only the automated generated tests exercised those code paths and found those bugs. So that's amazing. So we do believe that these benefits are great, and that's why we will continue to deploy P4 in this way for our switches. So that's all the learnings from the switches. So now let's see what's happening on the network virtualization world. So this slide shows how Google's network virtualization stack, data plane in particular, has evolved over the years. Every 10x improvement in speed has required us to re-architect our stack completely. And we believe what we have should serve us well for the next decade. But what you see here is on the first slide, on the first picture there, the Snap software NIC, that's really our software NIC. Snap is Google's version of DPDK. This is what we use internally to build user mode data planes. And what you're seeing here is from picture 1 to picture 2, it's really changing from going through the hypervisor to doing hypervisor bypass, and then more of the stuff is being offloaded to the NIC. The first model served us well, going through the hypervisor up to 10 Gbps, going from 10 to 100 required us to completely bypass the hypervisor and go directly to the NIC from our software and do more and more of the offloads. And now we're here where everything runs on the smart NIC. The slow path, the fast path, everything is all running on the smart NICs. This is currently running at 200 Gbps, and we believe this would be sufficient to take us to terabit per second host networking. So since this architecture will be with us for a while, new hardware will show up, and things will change underneath. And one of our biggest challenges is now, how do we adapt our software as the hardware will change underneath? So far, we were running everything in software, so as things changed, it didn't matter to our software as much. But now we are tied to the hardware a lot more. So therefore, one of our biggest challenges for the next few years is really making sure that our software remains portable across multiple NIC generations and possibly even different NICs. And porting is not easy. It's a multi-year effort, and that I'm talking just about network virtualization. If you think about all the software data plane applications we have in load balancers, firewalls, and many, like there's at least 10 different applications, if not more, all built on software using Snap. They all will want to take advantage of the offload capabilities of newer NICs in some shape or form. Without having a standardized model, without having a HAL, we're looking at a decade of porting work. So we really do need this HAL to work. And we believe that P4 has all the right building blocks to build this HAL. It gives us the APIs, it gives us a behavioral model, it gives us validation tests, so we can make sure that the controller code, the implementation, and the tests can all stay in sync. But what's missing? So are we done? We could just use it. There are language extensions that are needed, and people are working on those. But one key thing we believe missing is a high-performance P4 runtime. So in the switch world, the controller is remote. It's aware of P4, and it's programming the switches, and the rate of change is not that high. In network virtualization, the controller is local. The cloud controller isn't aware of anything about the hardware or P4, et cetera. It's talking more higher level, application level semantics. This is a virtual private cloud. This VM needs these features. And then it's up to the controller running on the NIC to realize that intent. So, and it gets involved in pretty much every connection. The rules are processed in the slow path for every connection, and then they are offloaded to the hardware. It isn't always every connection, but roughly that's the order we're looking at. In addition, we have bulk operations for live migration, syncing state across multiple different NICs, et cetera. So all of these mean we need a very high performance runtime. So do we think we can build that runtime? We believe so. The P4 community has done enough work that we have almost all the building blocks needed to build this runtime. So I still have the picture of our Snap local controller, which now is using a HAL that's built on this thing called P4 runtime local. This was a proposal at last year's workshop. It essentially removes gRPC, or all the remoting overheads from P4 runtime, and uses a multi-threaded serialization engine to serialize your protocol intent down to the P4 backend. So that, combined with TDI, which is really a simple abstraction, it just gives you tables and CRUD operations on tables, we think forms the right basis for building such a HAL. TDI frontend is available in open source, and vendors can build a backend based on their hardware. So with these building blocks, we think we can meet all of our objectives for this HAL. We can get high performance. I think people have demonstrated you can actually get to millions of table operations per second. This enables a variety of targets, whether they are manually compiled or manually written or compiler driven. So the TDI backend could be compiler generated, or it could be manually written, as long as, or tuned in other ways, including externs and whatnot. As long as it serves the same TDI front end, it can, our controller can use it. And it enables rapid development of features. We believe that by removing a gatekeeper or a static, which presents a static model of the pipeline, like for example, in case of Psi, there is a static model of the pipeline. So by removing that static model and directly interacting with hardware, we believe we can take advantage of hardware features more quickly without having to modify this common gatekeeper. So we think this this runtime will meet the needs. P4 has all the other tool chain that's necessary to build this HAL. So what would it take to kind of make this happen? We need to continue to invest in these tools, especially TestGen and P4 DPDK backend. So that work is ongoing. We just need to kind of double down on it as a community. In terms of users, I think more users should be adopting a TDI-based backend, whether you're using P4 to build your HAL or you're using a non-P4 HAL. So for example, Psi Dash could technically be built on top of TDI. TDI literature explains how that could be done. Or you have your own API. At the end of the day, everybody building a system will need some way to abstract the hardware, assuming they have more than one generation or more than one piece of hardware. So either you're going to use this or you're going to come up with your own. There's going to be some API that you use to abstract away the hardware functionality. And we need more, more targets. More vendors adopt it, more of this will be successful. So, that's really my proposal. That's really the pitch that, so far in Switch SDN, P4 played this dual role as a HAL as well as an SDK. We believe it will continue to be used as an SDK on switches that are P4 programmable, but P4 has an even bigger opportunity on smart NICs to be that HAL to program multiple different types of NICs. This enables NIC optionality, works for users like us as well as for different vendors, but we do need to work together, continue to, keep this community vibrant in order for this proposal to be successful. So with that, I think I'm done. I'm ready for questions. Yeah.
Parveen, great talk.
Thank you.
Quick question. You mentioned that your controller is involved in every connection that comes in. With that kind of an interaction, what type of CPS do you guys get?
So yeah, today it doesn't exactly get involved in every connection. Many of the flows are 3-tuple, but there is a degenerate case where it does get involved in every connection. Given all the optimizations we've done with Snap, we feel comfortable. We don't really run into connection per second issues. I wouldn't like to quote a number here, but it's not an issue for us today based on our software optimizations.
Okay.
But if it does ever become an issue, Krishna showed how you could offload some of that to the hardware.
Right.
On the IPUs we're using, it could be offloaded to hardware. So it's not necessary that the controller has to get involved, but that's the degenerate case, and we want to be able to support that.
Sure. Okay. Thanks.
Hey, thanks. Always good to see the way that you drive this forward, because you're the ones with the real problems at scale. And so being able to sort of point out how to best solve those problems through this approach and P4 runtime, the HAL, et cetera, I think is super useful. And thank you for coming and talking about it openly and publicly, because I think it really helps other people, whether they're in industry or in a research setting, to frame what are the problems that you understand at scale. So you made a call to action.
Yes.
Right. So, for test gen, DPDK, et cetera, and things that you would like to see, can you say a little bit about how Google can play a role in that? Because it would be wonderful if Google can be a part of that as well, and that we can all help bring in not only the vendors, but Google and your competitors too, because it's exactly the kind of forum that can do that. So what are your thoughts?
Yeah, I think we are involved, and we want to continue to, on all fronts, continue to enhance the language by participating in the language group to add extensions for what we need on the SmartNICs, as well as contribute to test gen, to behavioral model, and maybe also contribute our models of the pipeline that we use in different scenarios. So I think those are some of the ways in which we would like to contribute and have more open interaction with everybody. It's just a matter of priorities. As you know, everybody's going through this big change, a lot of pressure from AI, ML workloads, and so on. And but as soon as we have cycles to contribute more, I think we would definitely like to do more and keep doing what we've been doing so far.
Great. I think there's a massive amplification that comes from your involvement, so that has a very good scaling effect when you can. So thank you.
Yeah, great. Thank you.
So this may be off target a little bit. I loved the idea of rallying around TDI. It kind of strikes me as back to the future. Do you see it that way? It's almost as though, if we could just if we could start with OpenFlow and we have these tables of rules, but we could write the language that let us change what the rules are over time, we'd be done. And that's kind of what a HAL is when it's a TDI based. Is that?
Except it does have a P4 specification from which it was generated.
Right.
So it does have that, the specification and the behavioral model aspects to it, which is what, some of the key.
Well, it's the ultimate tension, because as a HAL, you want to mask all those differences below it.
Yes.
And that's what OpenFlow originally was intended to do.
Right.
Except, of course, there are all those differences. But now I can change the difference with the P4 program, but it's still a table. It's interesting how these things come around.
Yes, that's true. Yeah, and I think in a way, in systems, we have all these. It's a classic problem. Operating systems are full of these interfaces and different drivers. So this is kind of going back to a similar model, except there is a more formal definition.
One more round of right.
Yes.
Exactly.
Yeah, a couple of questions actually.
Yeah.
Is there a reason why the VMM is still sitting in the host in your diagram that you showed?
No, it's just, I would say, matter of time.
It's chewing those CPU cycles, right, that you could make money from?
Potentially. Potentially, yeah. I think it could be offloaded, and there are scenarios where it would be offloaded, but.
Okay. I have a feeling this may not apply to a use case. You probably have very few hardware drivers you have to deal with. But if based on your HAL diagram, if you have a lot of vendors underneath, do you see a unification transforms that could be maybe used? I'm not sure if TDI is sufficient for that, but it's runtime things.
Right. Well, back in the day, I worked on Windows, which supported like 2 million drivers. So I don't know. I think it's possible that you can support, a variety of drivers under the same interface if it's designed well. It does take time. Like we do have drivers for basic NIC functionality. We also started an effort in OCP to standardize on what are some of the NetDev offloads that the driver should implement. So I think if it's specified well, comes with a good set of APIs, and most importantly, a validation and testing infrastructure. I think if you have those, then you can make it work, assuming the economics work out, right?
So we're actually
in the
trying
cloud,
to
it's
solve
very
this.
different, but yeah.
We are trying to solve this in P4TC. The challenge is runtime. When some hardware may have to split tables, others may have to merge tables, sort things.
Yes.
You're doing a runtime thing. If you have 1 or 2 drivers, that's an easy thing to deal with. But if you have 200, it's not just merely the API, but how you merge from the P4 abstraction to a specific hardware.
So yeah, I think the only way to scale that would be for you to offload the work to the drivers, to the people who are providing the drivers.
Yes.
If there's enough economic incentive for them to participate in this ecosystem, I think they will do that.
Okay.
But if there's no economic incentive, then I think.
Okay.
Yeah.
Somewhat riffing on Larry's question. So if you think about the call stack down from, okay, you've now got a P4 runtime local layer to TDI down. If you think about the language to manage and manipulate tables, which is really kind of what we're talking about here. You mentioned CRUD, but then at least in my experience, pretty soon you want transactions. I mean, when you want transactions, you get to roll back and then you start to query the thing. And I'm throwing a line in the sand here to point to a 2008 discussion that Ben Pfaff and I had on the OpenFlow mailing list at the time, saying we should throw this all out and just use SQL. So my claim is at some point in the future that will actually become true, that we'll effectively implement most of what we want for table management and manipulation, and we'll have basically should have just use SQL. And so I'll throw it out there for you to comment on.
Yeah, well, we've had quite a bit of success with NoSQL, So it could go for a while. So I think that remains to be seen. Maybe it will evolve to be much more complicated than the simple picture shown here. I think that picture is already way too simpler than the reality. But what kind of transactions we would need? Maybe there's just a few things I can think of, like during live migration and hitless upgrades, scenarios like that. But I don't know if we need transactions in the general case. We've had to kind of partition the problem and do away with transactions for performance for multi-threading already. So I think some of those things should be applicable even here. So wherever we can partition and avoid transactions, I think we'll continue to do that. But there will remain some use cases where that's necessary.
Thank you for entertaining my silliness.
I think he has asked part of my question already. So the question is very basic one. You talked about the TDI. So the P4 runtime already supports read and write semantics with atomics, with batching and so on. So is this TDI make sense only if we have a P4 local, or still you have across boundaries? Like if the box already supports P4 runtime, which has read and write semantics, will that be sufficient? Or Google will expect TDI also?
Well, so because we're writing the P4 runtime local,
Okay.
then we are targeting a TDI API.
Okay.
So therefore, we are expecting TDI. But technically, the local controller, it's only interacting with the P4 runtime. It doesn't know anything about TDI. Right?
Okay. The other question is, can you expand more on using P4 as a HAL between the controller and can you go back
Oh, yeah.
a couple of slides? One more.
This one or?
I think one more. Okay, yeah. I think you had a slide where you have the Orient controller.
Oh, yeah. This one, the switch SDN. Yes.
Yeah. So I think you're mentioning a couple of times using P4 as a HAL API between the controller and the other part, so that your controller can work with multiple vendors. So it's all about the P4 definition. So you expect this P4 specification, the program your controller assumes has to be supported by all the vendors, right?
That is correct, yes.
Okay, thank you.
Hey, do you have any plans for open sourcing P4 runtime local as a spec or as an API, or what about Snap? Do you have any plans of open sourcing?
I think Snap is, so we have to look at kind of what's the benefit, cost-benefit analysis of open sourcing it. It's a lot of code, and it's very embedded in a lot of Google technologies, so it's not easy to open source it. I mean, there is the open source equivalent, that's TPDK, so it's unclear if we will get a lot of value out of open sourcing it. It'll be like multi-hundred years effort. It's not going to be easy to disentangle it from all the Google ecosystem and make it open.
What about the P4 runtime local as a spec?
I think that, that's a possibility. I think we would like it if there is an open source implementation that meets our needs and is beneficial to the community.
Thank you.
Yeah.
You mentioned here about some challenges, yes, like the batching, yes, reading of the million statistics and so on. And is your plan, for example, to keep the, for example, batching only inside of the P4 runtime and the overall TDI stuff, and for example, LLD will work like it works today by the single operation, yes? Here's a single access, or do you want to modify both the P4 runtime, TDI, and LLD, yes, to support, for example, batching, and it is just, what is your plan here?
I don't really have that detailed a plan. So I think it will all depend on, once we start to build it and measure it, we'll see where it ends up. And if batching needs to flow all the way down, then that's what we will have to do. So at this moment, I don't really have a specific answer for you.
Okay, thank you.